Good evening, everybody. Asim is my name. I want to explain the plastic deformation analysis of high beam, and this is one of my projects that I have to do. And I want to explain it using ANSYS to model the high beam plastic deformation and explain the process that I went through on ANSYS. So, plastic deformation is a permanent deformation that occurs as a result of load that is being applied on the I-beam exists or is more than the ultimate or the yield strength of the I-beam or the structural material that we are trying to model. So the load that the strength that I want to apply on this high beam has to be more than the yield strength of this material before this plastic deformation can occur. And this is what happens when we have the material when we have a failure in any structure, so which means the force or the stress that is being given or that is being applied to these structures is more than the yield strength of that structure, and we don't want that to happen. That's why we need to keep our load below the yield strength of the material that we are using. This is the equation of the plastic deformation. This is the plastic stress, and this is the plastic strain equations. And this equation will be the equation that will govern our analysis in ANSYS. If my analysis does not agree with this equation, which means my analysis is not correct, or is something that I need to do to make sure that I have the correct analysis. So this is my model. I want to use high beam in a cantilever conditions, which means one end is fixed and the other end is free, and the length of my I-beam is going to be 500 millimeter, and the load that I will apply on my I-beam is not going to be a constant load. It's going to be a load that is not constant. As you can see, the load increases as the length of the beam increases as well. This is the shape of the I-beam, and this is going to be the dimension of the I-beam that I will use. I got this information from this website. We have different sizes of I-beam. So we have different sizes of high beam. We have different sizes of high beam, and in that case, these are the dimension of the I-beam that we have. So with that, I chose this dimension to be the dimension of the I-beam that I will use, and this will be the dimension that I have to put in ANSYS to create my model. And this information was getting from this site, as I told you earlier on. And this is the ANSYS environment. I created my I-beam in ANSYS modeler. It's very simple. Just go to the sketching. When you go to the sketching, there are different cross-sectional area that we can choose. Go to the concept. When you go into the tools and you see the concept, under the concept you can choose any of the cross-sectional area that you want, and you can extrude that cross-sectional area with respect to the dimension that you want. And that's what I did there. This is my beam that was created in ANSYS. This side is my fixed end. As you can see in ANSYS, see this sign says fixed support. This side right here that is blue is my fixed support, and this end right here is free, and this place is going to be the place that I will apply my loading condition. So this is my boundary condition right here. This end is fixed, it's not moving, and the other end is free, so it can move. It can move in X, Y, Z direction, whichever direction that I want it to move. But basically here is going to move in a Y direction because my load will be acting downward. So this is my loading condition. As you can see, I loaded my beam from here to this place from 0 to 500. So at this point at 500 I have my load to be 4 megapascal, but at this end I have my load to be 0. So this is my loading condition. That's why you see the load increases as we go in Z direction, and this end is the maximum while this end is the minimum. I apply the pressure in ounces, and this is the pressure of this amount that varies from 0 to 500, from 0 to 4 megapascal. And this is the graph of my load. As you can see, this shows how my load increases with respect to Z direction, which is 500. It's very simple as well. Go to the structure and right click, insert the pressure. You can just insert the pressure and just make the pressure in y direction, negative y direction. Honestly, if you do that, you are trying to make the load as a concentrated load, but in this case you have to choose tabular form, and you just need to input this value right here before you can get the load to be in this shape. This is the loading condition as well with respect to time. So the first step is right here, 0 step is right here. The first step is that is going to increase the load up to the 500 millimeter, and the second step is that the load is going to release because we want to do plastic deformation. I will show you the graph. When I show you the graph, you will understand this better. It's going to be 2 steps. The first step is to load the beam up to plastic region, and the second step is to release the load so that you can see the shape of the plastic region with respect to the elastic region. So this page just shows the stages. This stage is the first stage, the stage of loading, and this stage is the stage that we are releasing the load from this beam. And after perform my analysis and solve the problem, this is the deformation of the high beam. The first set of the deformation is going to be elastic, and since my load is higher than the yield strength of the material, so the high beam became plastic deformed. So as you can see, the system experienced plastic deformation as a result of the load that is being higher than the yield strength of the material. So this is the plastic deformation, and this is the strain deformation. So the strain deformation of this system, the maximum is this 0.0015745, and the minimum is something that is very small, up to times 10 raised to power minus 10. So as you can see, so this is the strain deformation of this system. As well, this is the for missing stress deformations. As you can see, my material that I use in ANSYS is structural steel. The yield strength of this material is around 250 megapascal, and you see the strength, the maximum strength, the maximum stress that I have here is 3114 or 3115 approximately. Excuse me. It is higher than 250 megapascal, and that's why this material deformed plastically. These are the data during the deformation, the stress, the strain, the increasing in time, as well as the condition changes. This page right here just shows the maximum and minimum deformation, and each of these place. So this is called probe. I just try to know where is my maximum and minimum stress. You can just click anywhere. Is going to show you the value when you click on probe in ANSYS, and just click anywhere on the analysis that you are on, the analysis module that you are doing. This is my minimal, this is my maximal, and these are the value within those two, within that range between the minimal and maximum. This is the plastic deformation graph that I wanted to show you earlier on, that I mentioned. If you see this graph, you see from here to here is elastic region, and from here to here from here to here is elastic region, and from here to here is plastic region. See, from here to this place is when we load the material, when we apply the load, and from here to here is when we release the load, which means from here to here is first step, and from here to here is the second step. And that is why it is very, very important to do like two steps, because it's going to load and unload. If we don't unload, we are not going to have this side right here. But from here to here is the plastic region, while from here to here is the elastic region of my system. And this is the data that generated in ANSYS, showing every increments in time, in strain, in stress, and in strain as well. So this data gave this graph right here, and this is the graph that we actually have to get. If we don't have this graph, which means our material does not deform plastically, and that does not correlate with the plastic deformation that we aim to do. But as you can see, this graph it shows the same thing that we want, because we have the elastic region from here to here, and we have the plastic region from here to here. I will show you the video of the deformation as it goes, as you apply the load, how this beam changes from one stage to another, from first step to the second step, and finally the permanent deformation. This is just the video recorded or capture in ANSYS. I just want you to see how the beam deform after applying the load, and this side is fixed, and just solve the problem. This is how the beam behaves. So this is, you can see it right now. This is permanent deformation right now. You see it right now. Let me play it again. It's not permanent until this place right now. It shows you, it tells us that the load that we apply on this beam is higher than what the beam could bear, and that's why we have the permanent deformation at the end of the day. Thank you very much for watching my video. I really appreciate. The next video that I will make, I will walk you through how I did all this in ANSYS. I just wanted to do the presentation, and that's why I just capture my deformation in ANSYS and just do the presentation. But the next video, I will show you how I input my parameter, my ANSYS analysis, my meshing, and some other things that I have to do in ANSYS before I can get to this place. I will walk you. I will walk you through everything so that you can see how everything is made or is done in ANSYS. Thank you once again. I really appreciate. Have a nice day.